Hi, welcome to educator.com. We're going to talk about the ChiSquare Goodness of Fit test. So we're going to spend our time right in here. All right, so there's a new twist on hypothesis testing. It's not totally different. It's still very, very similar, but there's a subtle difference. And today we're going to start off with the ChiSquare Goodness of Fit test. Basically, let's think about hypothesis testing in general. In general, you want to determine whether a sample is very different from expected results. That's the big idea of hypothesis testing. And the expected results come from your hypothesized population. If your sample is very different, and we usually determine that with some sort of test statistic and looking at how far it is on the test statistics distribution, right? And we look at whether it's past that alpha cutoff or the critical test statistic, right? And then we say, oh, this sample is so different than would be expected given that the null hypothesis is true, that we are going to reject the null hypothesis, right? That's usually hypothesis testing. Goodness of Fit still takes that idea. We're going to look at whether a sample is very different from expected results. But the question is, how are we going to compare these two things? We're not going to compare means anymore. We're not going to look at the distance between means. Nor are we going to look at the proportion of variances. That's not what we're going to look at either. Instead, Instead, we're going to determine whether the sample's proportions for some categories, right, are very different from the hypothesized population's proportions, right? And the question will be, how do we determine very different? And here's what I mean by determine whether the sample proportions are different from the hypothesized population proportions. So here, I'm just going to draw for you sort of schematically what the hypothesized population proportions might look like. So this is just sort of the idea. So you might think of the population as being like this. And in the population, you might see a proportion of 1/3 being blue, 1/3 being red, and 1/3 being yellow. Now, already, it's hard to think about, like you could already sort of see, well, we can't get the average of blue, red, and yellow, right? Like what would be the average of that? And how would you find the variability of that, right? So already we're starting to see why you can't use t-tests or ANOVAs. If you can't find the mean or variance, you can't use those tests, right? So if this is what our hypothesized population looks like, then when we get a sample, when we get a little sample from that population, boop, right? We want to know whether our sample proportions are very different from the hypothesized proportions or not. So let's say in our sample proportion, we get mostly blue, a little bit of red, a little bit of yellow. So let's say 60% blue, 20% red, 20% yellow. Are those proportions different enough from our hypothesized proportions, right? Another sample we might get, right, is half blue and half red and no yellow, right? Is that really different from our hypothesized proportions? Another sample we might get might be only like 1/10 blue, and then 40% red, and then the other half will be yellow, right? So in something like that, we want to say, is this really different from these hypothesized population proportions? And so that's what our new goal is. How different are these proportions from these proportions? And then the question becomes, okay, how do we determine whether something is very different, right? Is this very different or just sort of different? Is this very different or just kind of different, right? How do we determine very different? That's going to be the key question here. And that's why we're going to need the ChiSquare statistic and the ChiSquare distribution. All right. So we're changing our hypotheses a little bit. Now the null hypothesis is really about proportions. And here's what we're talking about. The null hypothesis is now this. Is it that the proportions in the population are real population that we don't know? Question mark, population, right? Boop, we don't know it. Will this population be like the predicted or theorized proportions, right? And so here we're asking, is this unknown population like our known population, right? And that should sound familiar because that's sort of the fundamental basis of inferential statistics. So that's our new hypothesis, new null hypothesis, that the proportions in the populations are like the predicted, will be like the predicted population proportions. They'll be the same, right? Remember, sameness is always the hallmark of the null hypothesis. Alternatively, you want to say at least one of the proportions in the population will be different than predicted, right? So going back to our example, so if our population, our hypothesized population is something like, one third, right? Maybe what we'll find is something like, in our sample, we'll have 1/3 blue, right? But then some smaller proportion, like, 15% red, right? And then the rest being yellow, right? Now, the 1/3 should match up, right? The 1/3 matches up. But what about these other two? And so in the alternative hypothesis, at least one proportion in the population will be different from the predicted proportions, right? So it just has to be one guy that's different. All right, so just to give you an example, let's turn this problem into a null hypothesis and an alternative hypothesis. Okay, so here it says, according to early polls, candidate A was supposed to win 63% of the votes, and candidate B was supposed to win 37%. When the votes were counted, candidate A won 340 votes, while B won 166 votes. So here, just to give you that picture again, the null hypothesis population was that candidate A, I'll color A in blue, candidate A should have won 63% of the vote. And candidate B, well, I'll color in red, should have won 37% of the vote, right? So what would be our null hypothesis? Well, our null hypothesis would be that our unknown population will be like this predicted, the proportions in my unknown population will have the same proportions as our predicted population, right? So here we might say something like A's votes, A's proportion of votes, of the actual real votes, should be like this, the predicted population, right? And B's proportion of votes, sorry, this is a little small, should be like predicted population, right? So it's saying A's proportion, the real proportion of votes, should be like this, and so should B's. B's should be like this, right? The other way you could say it is that the proportion of votes the real proportion of votes should be like the predicted proportion of votes, right? And then you could just say for every single category, for both A and B. So what would be the alternative version of this? The alternative would say at least one of the proportions, one of the categories, either A or B, one of those proportions will be different from the hypothesized proportion. And in fact, in this example, if one of them is different, the other one will be different too. Because since we only have two categories, if we make one really different, then the other one will automatically change, right? But later on, we might see examples where we have like 3 or 4 or 5 categories. And so in those cases, this will make more sense. Okay, so now let's talk about how to actually find out if our proportions are really off or not, right? Are our proportions statistical outliers? Are they deviants? Are they significant, right? Do they stand out, right? That's what we want to know. And in order to do that, we're going to have to use a measure called the chi-square statistic. Instead of the t statistic, which looks at distance away in terms of standard error, instead of the f statistic, which looks at the proportion of the variance we're interested in over the variance we cannot explain, the chi-square does something different. It's now looking at expected values. What would we expect? And what did we actually observe? Right? And so the chi-square is going to look like this, right? So be careful that you don't, usually it's like an uppercase X, and it looks a little bit different than like just a regular letter X. It's usually a little more curvy to let you know it's chi-square. So the chi-square is really going to be interested in the difference between what we observe, right? The actual observed frequencies or percentages minus the expected frequencies, right? So when we're looking at observed versus expected, this is what we see in our sample, right? And this is what we would predict given our hypothesized population. So this is that predicted population part, right? So we're interested in the difference between those two frequencies. Now, although you could use proportions as well, you can only do that if you have the same, if you have a constant number of items. So you probably are safer to go with frequencies because those are sort of like weighted proportions. So you probably want to go with that. All right, so we're interested in this difference. But remember, when we look at this difference, sometimes they're going to be positive, sometimes they're going to be negative. And so what we do here, as usual in statistics, is we square the whole thing, right? But we also want to know about this difference as a proportion of what was expected. Right? And we want to do this for every category, for the number of categories. And I goes from 1 to the number of categories. And there's actually an I down here for everything. So what this is saying is that for each category, right, each proportion that you're looking at. So in our sort of toy example with the red, blue, and yellow, right? Blue, red, yellow, right? In this example, we would do this for blue, we would do this for red, and we would do this for yellow. So number of categories. So categories really speak to what are the proportions made of. And so in here we have 3 categories, so we would do this 3 times and add those proportions up. And we want to eventually be able to find the observed frequencies and the expected frequencies. Now, in the example that we saw with the voting for candidate A and B, one of the things I hoped you noticed was that the observed frequencies were given as just number of votes, how many people voted. But the expected frequencies was, hypothesized population, that was given as a percentage, right? So you can't subtract votes from percentage. You have to translate them both into something that's the same, right? And so in that, it's helpful to change the expected percentages into expected frequencies, right? And there's going to be another reason for changing it into expected frequencies instead of changing the observed frequencies into observed proportions. And I'm going to go into that a little bit later. So here's what I want you to think of this as. It's really the squared difference between observed and expected frequencies as a proportion of expected frequencies, right? And you want to do that, and you want to sum that over all the categories. Once you have that, then you get your chi-square value. Now let's think about this chi-square value. If this difference is very, very large, right? So observed frequencies are just very different than expected ones, right? If that difference is very large, you're going to have a very large chi-square, right? Also, if this difference is very small, they're really, really close to each other, then your chi-square is going to be very small, right? So chi-square is giving us a measure of how far apart the observed and expected frequencies are, right? Also, I want you to see that the chi-square cannot be negative. First of all, because we're squaring this difference, right? So this numerator cannot be negative. Not only that, but expected frequencies also cannot be negative because we're counting up how many things we have, right? How many things we observed. And so this also cannot be negative. So this whole thing cannot be negative. So already we see in our mind the chi-square distribution will probably be positive and positively skewed because it stops at 0. There's a wall at 0. Okay, so now let's actually talk and draw the chi-square distribution. So imagine having some sort of data set and taking from it over and over again samples. So you take a sample and so you have this big data set, you take a sample and you calculate the chi-square statistic, right? And you plot that. So you plot that. And then you put that back and you take another sample and you take the chi-square, plot it again. And do that over and over and over and over again. You'll never get a value that's below 0, right? And you'll get values that might be way higher than 0 sometimes, right? But for the most part, they'll be clustered over here. So you'll get a skewed distribution. And indeed, the chi-square distribution is a skewed distribution. Now here, when we look at this, you might think, hey, that looks sort of like the F distribution. And you're right, overall in shape, it looks just like the F distribution. And in a lot of ways, we could apply the reasoning from the F distribution directly to the chi-square distribution. For instance, in the chi-square distribution, our alpha is automatically one-tailed. It's only on one side. And so when we say something like alpha equals 0.05, this is what we mean. We mean that we'll reject the null when we have a chi-square value that's somewhere out here or out here or out here. But we will fail to reject if we get a chi-square value in here from our sample. Now, this chi-square distribution, like the F and T distribution, it's a family of distributions. It's not just one distribution. The only one that is just one distribution is the normal distribution. The chi-square distribution, again, depends on degrees of freedom. And the degrees of freedom that the chi-square depends on is going to be the number of categories minus 1. So if you have a lot of categories, the chi-square distribution will look different. If you have a small number of categories like 2, the chi-square distribution will look different. All right, so let's talk about what alpha means here. The alpha here is this set significance level. We're going to say we are going to use this as a boundary, a cutoff, so that if we have a chi-square from our sample that's bigger than this boundary, right, then we will reject the null, right? What is the difference now with p-value? Now the p-value says this is the probability. So we might have a p-value somewhere out here, or we might have a p-value somewhere here, right? The p-value is going to be very similar to other hypothesis tests, what the p-value means in other hypothesis tests. Basically, it's going to be the probability of getting a chi-square value larger, more extreme, right? And in this case, there's only one kind of extreme, positive. Larger than the one from our sample, but under a condition. Remember, in this world, which one is true? The null hypothesis is true. Given that null hypothesis is true. So considering if the null hypothesis were true, this would be the probability of getting such an extreme chi-square value. One that's that large or larger, right? That's what we mean. So in that way, the p-value is from our data, while the alpha is not from our data. It's just something we set as the cutoff. Okay, so there are some conditions that we need to know before we use the chi-square. When we use the chi-square, you can't just always use it. There are conditions that have to be met. So one of the conditions of the chi-square is this. Each outcome in the population falls exactly into one of a fixed number of categories. So every time you have some sort of case from the population, right? So let's say we're drawing out votes, right? Each vote has to fall into one of a fixed number of categories, right? So if it's 2 candidates, it's always 2 candidates for every single voter, right? So we can't compare voters that had 2 candidates versus voters who had 3 candidates, right? Also, these have to be mutually exclusive categories. One vote cannot go to 2 candidates at once, right? So they have to be mutually exclusive. You gotta vote for A or vote for B. And you can't opt out either. They can't vote for nobody. Or else nobody has to be one of the fixed number of categories ahead of time. Okay, so the numbering is slightly off here. But the second condition that must be met is that you must have a random sample from your population. That's just like all kinds of hypothesis testing, though. Okay, number 3, the expected frequency in each category. So once you compute all these expected frequency in order to compute your chi-square, that needs to be each cell, each square, needs to have an expected frequency of 5 or greater, right? Here's why. You need a big enough sample, right? If you have too small of a sample, you're going to get expected frequencies less than 5. Also, you need big enough proportions, right? So let's say you want to compare proportions that are like, like one candidate is going to be predicted to win 99.999% of the votes, and the other candidate is only supposed to win 0.001% of the votes, right? And you only have 5 people in your sample, right? And so you need to also have big enough proportions, and these balance each other out. If you have a large enough sample, then your proportions can be smaller. Also, if you have large enough proportions, then your sample could be smaller, right? So they sort of play off of one another. And the final condition is not really a condition. It's just sort of something I wanted you to know as a rule. The chi-square goodness of fit test. So that's all we've been talking about so far. This test actually applies to more than 2 categories. You don't just have to have 2 categories. You could have 3 or 4 or 5 or 6, but they do need to be mutually exclusive, and each outcome in the population must be able to fall into any one of those. Okay, so those are the conditions.